If you take a massive, like trillion parameter AI model, spin up 1,000 GPUs, and just feed it the entire internet, it actually gets dumber.
Oh, yeah, it completely degrades.
Right, but if you ruthlessly delete 50% of that data before you even start the training, suddenly it becomes a genius. Welcome to the deep dive. It's late, you're likely staring at an IDE, maybe compiling some code, or just letting your mind decompress. And you've joined us to look at something foundational.
And we are stripping away the flashy neural network architectures tonight.
Exactly. The parameter hype is gone. We are looking at the unsung hero of the AI revolution, which is the data pipeline. We've got this stack of AI lab engineering notes, data curation research papers, architectural leaks, and the reality they paint is just stark.
It really is a profound engineering reality check.
Yeah.
Because the underlying premise of every major model today is that the raw internet, untouched, is fundamentally, well, mostly garbage.
It's an absolute ocean of noise. I mean, we are talking relentless SEO spam, syndicated boilerplate text, completely toxic outputs, and just massive amounts of personally identifiable information.
Yeah, you can't just open a socket to the web, point a fire hose of JSON at a server cluster, and expect this highly reasoning, nuanced engine to emerge.
You just get a chaotic, babbling mess.
Precisely. To feed an LLM properly, developers have to build an absolute gauntlet of a pipeline. It's this rigorous, multi-stage filtering process designed to, distill petabytes of chaos into a concentrated signal.
So let's walk through that gauntlet, because before we even attempt to measure the quality of a piece of text, we have to deal with the sheer volume of redundancy. The first layer is deduplication.
The Great Purge.
Right. Now, for the software engineers listening, when we think of finding duplicates, we instantly think of cryptographic hashing, like SHA-256. You run a hash on a file, and if the hashes match, they are identical. But you can't use standard hashing on internet data, can you?
No. Standard hashing completely fails at this scale,
Yeah.
and in this specific context anyway. Because with a cryptographic hash, if you change a single comma or, add a single whitespace character, the resulting hash is radically different.
The avalanche effect guarantees it.
Exactly. But internet duplication is rarely byte-for-byte identical.
Right, because of the wrappers. Like, you might have a core Reuters news article syndicated across 500 different regional news sites. The core text is exactly the same, but one site injects a JavaScript banner ad at the top, another adds a different author byline.
And a third one appends a subscribe for more footer at the bottom.
Exactly. So a standard SHA-256 algorithm looks at those 500 pages and declares, hey, these are 500 completely unique documents, let's keep them all.
Which is useless for our pipeline. We need algorithms that can detect structural overlap. And that's where the engineering notes detail the use of min-hash and LSH, or locality-sensitive hashing.
Let's get into the mechanics of that, because it's such a brilliant workaround. How does min-hash actually survive those minor edits to realize it's looking at the same core article?
Well, it relies on breaking the document down into overlapping slices, usually called n-grams or shingles. Imagine taking a sliding window of, say, 5 consecutive words and moving it across the entire document, one word at a time.
Okay, so like the quick brown fox jumps, then quick brown fox jumps over, and so on.
Right, exactly. So you generate a massive set of these n-gram shingles for a document. Then min-hash applies multiple random hash functions to this set, but instead of keeping everything, it only records the minimum hash value produced by each function.
Oh, wow. So you are mapping the structural DNA of the sentence flow rather than just validating the final binary file.
Perfectly stated. It creates a highly compressed signature of the document. And the mathematical magic here is that the probability of 2 documents having the same minimum hash value is exactly equal to their Jacquard similarity.
Wait, Jacquard similarity?
Yeah, meaning the ratio of shingles they share versus the total shingles they have.
Ah, okay. So if 2 documents share, like, 80% of their n-grams, their min-hash signatures will be overwhelmingly similar.
Yes. And then locality-sensitive hashing groups these similar signatures into buckets. So the pipeline can look at a bucket of 500 syndicated articles, recognize the high Jacquard similarity, and say, we only need to keep one representative sample of this text.
The scale of what this wipes out is staggering. Looking at the curation papers, running this min-hash and LSH purge removes anywhere from 30 to 50% of the raw web data. Just gone.
Poof. Half your data set vaporized.
Vaporized before the GPUs even spin up for training. But here's where I want to push back a bit. Let's look at this from a learning perspective. If I am mentoring a junior developer, right, and I show them a clean, elegant design pattern 10 times, the repetition reinforces good habit.
Sure, it builds a mental pathway.
Right. So why does an LLM penalize repetition? I mean, shouldn't seeing a factual statement 10,000 times solidify it as truth rather than hurt the model?
That is a very intuitive comparison, but it completely breaks down when we map it to neural network gradients. We naturally conflate human memory reinforcement with machine learning weight updates.
Because they aren't the same thing at all.
Not at all. When a junior developer sees a pattern 10 times, they extract the abstract concept. When an LLM sees the exact same string of text 10,000 times, it doesn't extract a concept. It aggressively biases its parameters toward predicting that specific sequence of tokens.
Oh, so it overfits.
It massively overfits. It flattens the gradient landscape around that specific phrase.
Oh.
If it reads the exact same promotional boilerplate over and over, it starts to treat those specific statistical token transitions as the most important pattern in its universe.
It just loses the flexibility to generalize.
Exactly. It becomes a localized echo chamber.
Right.
Instead of learning the broader concept of a sale, it just aggressively wants to autocomplete the phrase, "Click here for 50% off."
That makes so much sense. And on top of that, you are burning incredible amounts of compute.
That's the hard engineering constraint right there. I mean, you are paying thousands of dollars an hour in GPU time. Processing 10,000 identical documents mathematically damages your model's ability to reason broadly, and it wastes millions of dollars in matrix multiplications to do it.
So deduplication forces the model to learn a wider variety of unique concepts rather than just memorizing the internet's most common spam.
Exactly.
Okay, so we've run the min-hash purge, we've sliced the n-grams, checked the Jacquard similarity, and deleted half the internet. But here is the trap. Removing duplicates just leaves us with unique text.
Right. Which isn't necessarily good text.
Exactly. A randomly generated string of toxic garbage or a totally bespoke, chaotic SEO keyword dump is technically unique. So now we have a pristine, deduplicated mountain of total trash. How does the pipeline mathematically distinguish between a high-quality historical essay and a unique spam bot?
That transition is one of the hardest parts of the entire pipeline. We move from establishing uniqueness to the much more abstract task of establishing value. This is the quality filtering phase.
And the research highlights two primary technical methods here, right? Classifier-based filtering and perplexity scoring.
Yes. And perplexity scoring is really the fascinating one here.
Let's dive deep into that. Because as an engineer, evaluating the quote-unquote quality of petabytes of text sounds like an infinitely subjective nightmare. But perplexity gives it a hard mathematical definition based on probability distributions.
Right. So in information theory, perplexity measures how well a probability model predicts a sample. For an LLM data pipeline, perplexity is essentially a measure of how surprised a baseline language model is by a sequence of tokens.
Let's break that down into token entropy. If we have a sequence of words, the model calculates the cross-entropy loss across that sequence. So if the text says the server is down due to a memory...
The probability distribution heavily favors the token leak.
Right. And if the next token is indeed leak, the entropy is low. The model is not surprised. That's low perplexity.
Yes. To filter the massive raw data set, developers take a smaller, highly optimized, trusted language model. Usually one trained exclusively on extremely high-quality, verified data like Wikipedia or curated academic journals.
And they run the raw web text through the smaller model.
Exactly. If the raw text flows naturally, uses standard grammar, and maintains a coherent semantic structure, the baseline model predicts the tokens easily. The perplexity score is low, and the pipeline keeps the document.
But if the text is a unique SEO dump that reads, buy cheap server RAM, download finance fast shoe, the token probability distributions are just chaotic.
They are all over the place. The cross-entropy loss spikes, the baseline model is highly surprised, the perplexity score shoots through the roof, and the system just throws that document in the trash.
That is such an elegant mechanism, and you pair that perplexity filter with specific classifiers, right? Like algorithms designed specifically to hunt down hate speech, explicit content, or code blocks that are actually just malicious payloads.
Yeah, and then you have a rigorous quality net. But, as the data curation papers make very clear, this is a treacherous tightrope walk.
Yeah, here is where it gets really interesting. Let's look at the cultural and linguistic bias introduced here, because this isn't just a clean math problem. It's an engineering constraint that basically dictates the model's entire worldview.
It absolutely does.
If we use a perplexity filter trained on formal, standard English to define what is mathematically high quality, Aren't we essentially hard-coding a dialect bias into the system?
We absolutely are, and it is a massive ongoing challenge in the field. Think about the baseline model used for scoring. If it was trained on Wikipedia and academic papers, its definition of low perplexity, its definition of good, is hyperformal, standardized English.
The baseline model expends a certain rhythm.
It expects rigid grammatical structures. So what happens when that perplexity filter encounters a brilliant, culturally rich forum post written in African American vernacular English, or a highly detailed technical explanation written in Scottish slang?
Or like a developer in Singapore mixing English and Mandarin idioms in a single paragraph.
Right. The token probabilities diverge from the standard Wikipedia baseline. The entropy spikes. The model gets surprised. High perplexity.
And the algorithm looks at those diverse linguistic expressions, registers the structural deviation as unpredictable, and flags it as low-quality noise. The pipeline just purges it.
It purges it completely.
That is wild. You set out to build a math filter to delete spam bots, and because of the baseline you chose, you accidentally delete a huge swath of human cultural expression. You mathematically erase entire dialects just because they don't look like a standard encyclopedia page.
It perfectly illustrates the tension in data curation. If you set your perplexity thresholds too loose, your final LLM learns to generate toxic garbage and hallucinate.
But if you set the thresholds too strict,
You create a model that is completely homogenized. It speaks in this hyper-sanitized, monotonous voice and completely fails to understand the nuance of how real humans actually communicate globally.
it really underscores that writing this pipeline isn't just about tweaking parameters to optimize compute. You are literally defining the boundaries of what the machine considers valid human knowledge.
And developers are constantly having to recalibrate these thresholds, introducing more diverse, high-quality baselines to try and catch the worst of the web while preserving the linguistic richness. It is a constant calibration.
Okay, let's assume the engineering team successfully walks that tightrope. You've run the Enneagram shingles through MinHash. You've survived the perplexity scoring without erasing all cultural nuance, and you've scrubbed the PII. You finally have a massive, clean, deduplicated vault of data.
A pristine vault.
But the process doesn't stop there. Because a pile of clean data isn't a model, you have to assemble it. And this brings us to the final and perhaps most heavily guarded secret in the entire architecture: the data mix.
The assembly phase. This is where the pipeline transitions from filtering to active curation. The exact proportions of web content, code, books, and academic text used in the final training run.
The architectural leaks show that this specific ratio is one of the most consequential decisions an AI lab makes. It is the proprietary formula. I mean, everyone has access to roughly the same raw internet. Everyone knows the math behind min-hash and cross-entropy loss.
But the true differentiator between a model that feels incredibly sharp and one that feels totally disjointed is this exact blend. Think of it like metallurgy. You are trying to forge an alloy. Web data is your iron. It's abundant. It provides the massive base of general knowledge, current events, and conversational fluidity.
It provides the bulk of the parameter's worldly context.
Exactly. But iron alone is too soft. It bends under the pressure of complex logic.
So you add carbon, and in this case, the carbon is code. And this is something I really want to unpack for a second. Why do we feed millions of repositories of Python, C++, L, and Rust into a language model that a user might only ever use to draft marketing emails or write poetry? Like, what does the code actually do to the model's brain?
It fundamentally alters the reasoning pathways. Because natural language is inherently ambiguous. It's full of idioms, subtext, and loose connections. Code is the exact opposite. Code is strict, deterministic logic.
It forces step-by-step execution.
Precisely. Think about how an attention mechanism works in a transformer model. When it trains on code, the attention heads have to learn that a variable declared on line 10 must be tracked and utilized perfectly on line 50 within a very specific scoping rule.
Right. If an IF statement opens, it must logically close.
Yes. So training on billions of lines of code forces the neural network to develop highly rigorous, long-range dependency tracking. It teaches the model how to hold a strict logical state over a long sequence of tokens.
So when the user asks the model to draft a complex marketing strategy, the model isn't just statistically guessing the next word. It's actually using the rigid logical scaffolding it learned from compiling C++ to structure the human argument.
Exactly.
It's using the carbon to reinforce the iron, high tensile steel.
That is exactly what happens. The code trains the reasoning engine. But you can't just use web data and code. You need books, too.
Right.
Books provide sustained, long-form narrative structure. They teach the model how to develop complex themes over hundreds of pages, rather than just the short bursts of attention you get from an internet forum.
And then you mix in the academic text, the peer-reviewed journals, the dense scientific papers. This forces the model to map citations to factual claims, teaching it rigorous factual density. So the engineering problem is finding the perfect percentage.
It's the ultimate recipe.
Right, like do you want your model to be 60% web, 20% code, 10% books, and 10% academic? Or do you push the code mix up to 35% to heavily boost its logical reasoning, knowing it might make its conversational tone a bit more rigid and robotic?
It is a delicate balancing act. And this leads directly to the core architectural takeaway from all these curation papers. It's a principle that completely upends how we thought about AI just a few years ago, which is that quality matters exponentially more than scale.
We hear so much about parameter counts and raw token volume, the race to 10 trillion tokens. But the math in the pipeline shows something else entirely.
It proves that a carefully filtered, masterfully mixed 1 trillion token dataset will routinely and significantly outperform a poorly filtered 10 trillion token dataset. The brute force era of big data, where labs just scrape every byte of text they could find and threw it at an endless rack of GPUs, that era is hitting a hard ceiling.
Because feeding a neural network 10 times more noise doesn't give you 10 times more intelligence. It just gives you a model that is 10 times more confused, and you burned tens of millions of dollars in compute to get there.
Exactly. It degrades the gradient updates.
Yeah.
The entire field has shifted into an artisanal data engineering game. The leading AI labs are no longer just trying to acquire more data. They're obsessing over the exact token entropy of their perplexity filters and the precise alloy mix of their final data sets.
They are functioning less like raw data hoarders and more like elite, hyper-focused librarians. It completely shifts the perspective on what makes these systems work. If you are a software engineer building on top of these models or trying to fine-tune your own local instances, deeply understanding this data pipeline, understanding the min-hash purges and the perplexity thresholds, is just as vital as understanding the transformer architecture itself.
Arguably more vital. I mean, you can have the most elegant, highly optimized neural network architecture in the world, but if you feed it toxic, repetitive noise, the attention mechanisms will just fail. Conversely, a relatively standard architecture fed pristine, perfectly mixed data can exhibit emergent reasoning that will absolutely shock you.
So let's pull all of this together. We took a serious journey through the gauntlet tonight. We started with the harsh reality of the raw internet. The syndicated spam, the wrappers, the noise. We watched the Enneagram shingles and Jacquard similarity of min-hash vaporize half the web just to break the echo chamber and save the gradient updates.
Then we navigated the friction of perplexity scoring, using cross-entropy loss to establish value while trying not to mathematically erase the complex dialects of human culture.
And finally, we hit the assembly floor. The highly secretive alloy of web, code, books, and academic text, proving that a pristine 1 trillion token dataset is the true king of the hill. It's an incredible engineering pipeline. But the story doesn't end here, because the research papers and architectural leaks point to actual specific names behind this data, legendary datasets that have physically shaped the foundational models you're interacting with every day.
Yeah, names like Common Crawl, The Pile, C4, FineWeb, and Red Pajama.
If you want to take the next step in understanding the systems you are building with, look into those names. Look at the data they contain, the specific mixing ratios they attempted, and the engineering hurdles they cleared.
Those datasets are the actual raw materials of the modern era. Understanding them is understanding the constraints of the models themselves.
As you wrap up your late-night coding session, or close down your terminal, or just stare at the ceiling letting all of this sink in, we want to leave you with one final thought to chew on, something the pipeline math forces us to consider.
Given everything we've unpacked tonight about the absolute supremacy of clean, highly curated data, if a meticulously filtered 1 trillion token dataset mathematically beats a 10 trillion token dirty one, and the exact ratio of that data alloy is a closely guarded secret, will the future of artificial intelligence truly be dominated by the companies that can afford to buy the most raw computing power? Or will it be dominated by the companies that master the art of being the ultimate librarians of human knowledge?